Being invited today by SIA to present on a topic that, considering the company I work for and the job that I do in terms of agronomy of NPKs fertilizer, I'm asked to speak to this topic quite frequently. And there's a chance that some of you in the audience, keeping in mind that a lot of you may have heard me speak as a guest speaker in some classes, that you may have seen some of these slides before. But I think we can always continue to learn and understand this whole topic in terms of marginal soils, specifically to soil salinity. What I'm going to present today, it's not the original research that we heard of from Jeff Shano earlier today, or a specific look at the programs that we heard in terms of the first speaker from the University of Calgary and the messy fields sort of approach, but rather more of a background to fundamentals of soil salinity and why we need to understand them better, and some very fundamental ideas in terms of ameliorating the problem. My job is to be an extension person for Nutrien, and this is my contact information. I'm always open to emails or phone calls or texts. So there it is, and I'll share it again at the end of the slideshow. We did just have a social media presentation. If you so care to do so, you can follow me on X, or as I would prefer to call it still, Twitter. So let's start off with talking about viability of land, viability of arable land in terms of profitability. If we take a step back and compare arable agriculture, producing annual crops, wheat or canola or other crops, to other businesses, we approach it quite differently when it comes to marginal soils. And I'm talking about marginal soils in terms of annual cropping. If you compare this business to an agricultural business like cattle production, cattle people understand profitability very well. If a cow is not productive, it's removed from the herd. It's culled. There's no room for a lack of profitability in a cattle herd. I've seen orchards. I've seen orchards in British Columbia, orchards in Ontario, orchards in other regions of the world, where you drive by and some of the trees have been cut down, and it's because they're not productive. If there's a species or a variety of orchard that fruit that is not profitable, it's simply removed and you start again. Certain stores, chains of stores, Tim Hortons or any other business, if there's a store that is not profitable, it's closed, and then you move the expenses that you've had in that specific store to your profitable stores. But in grain farming, we have a bad habit of just trying it again. We have unprofitable acres. We know they're unprofitable acres, but we just go back to it again next year and try it again. And I think that if we take a step back, we could make more money by farming less land, perhaps not reduce our total cost of production, but produce more production on less land if we use the money that we spend in growing crops more carefully. There's a lot of limitations, a lot of reasons that soils can be called marginal, and this is a list of them that I think are the primary soil limitations in agricultural soil in Saskatchewan, in Western Canada, really. Salinity is the big one, though. Salinity is a huge problem in terms of acres. It's huge problems in terms of yield limitation. It's very difficult to fix the problem. And on top of that, if it's not addressed as a problem, salinity can actually grow an acreage within a landscape. So we have to keep that in mind, that when we look at marginal soils, it tends to be salinity is the primary problem in Western Canada. Bit of a definition of salinity, it's simply an accumulation of an excess level of salts. Salts are not bad things in small quantities. Nutrients are taken up in salt form, a dissolved ion or cation or anions within the soil solution. And that's simply how plants absorb most nutrients. An excess of salts, whatever salt that type might be, can become a problem in that excess salts reduce the ability of plants to absorb soil moisture and may cause damage to the root system to reduce its ability to take up other nutrients. These are levels of thousands of pounds per acre of salts, salt pairs, uh, the cations of sodium, calcium, magnesium paired with sulfates, chloride, or carbonates. Uh, Primarily in Saskatchewan, we have problem with magnesium sulfate is terms of key salt pairs with perhaps a small amount of calcium sulfate as well. In other parts of the world, other salts become a greater problem. Sodium becomes a significant problem in alkaline soils, sodic soils in some parts of the world. We only deal with sodic problems with sodic soils primarily in salinetic soils, which I'm not talking about today. A couple of things that we can note, salts can carry electricity through water, and we'll need to understand that because that is how we primarily measure electrical conductivity. So when salts are dissolved in water, that water can conduct electricity more readily, and that then gives us a very easy means of measuring soil salinity. You can do this at home. I have a meter exactly like the one on the screen, and there's literally dozens of them available that you can buy for $50 or $60 each. It's not because people are manufacturing them for measuring soil salinity. They're made primarily for measuring conductivity of swimming pools and saltwater aquariums. But these are available and they're accurate. And if you want to have a soil salinity meter on your desk, you can own one. The graph here is simply a correlation of the measurements of saline soil using this very simple, inexpensive meter to having the same soil tested at a soil test lab. They're accurate and easy to use. Soil salinity can be used, or conductivity can be used to measure uh, soil parameters on a larger scale. In Saskatchewan, in Canada, we use EM38s quite frequently. Geonics, a company in Ontario, produces EM38s, a nice Canadian invention, and they can be a handheld EM38. You can put them in a sled to pull them around on a field to create maps, or you can mount them uh, in other means to again connect these EM38s to a software to create salinity maps or conductivity maps. Various machines are also sometimes used, perhaps not as common in Western Canada as some regions of the world or some regions of agriculture. But again, these are relying on the concept that soils can conduct electricity if to a greater capacity if they're saline. We then have scales of tolerance to salinity. Now, a warning, and I've noted here the term saturated paste. When you send a soil test to a soil test lab, a conventional soil test lab, they will not use a saturated paste to measure soil salinity. Rather, will use a ratio of soil and water. So you might see a reference to a 1-to-1 ratio, one volume of water to one volume of soil. It might be a 2-to-1 ratio. Some labs use up to a 5-to-1 ratio of water and soil. It's a very quick and easy way to dissolve those salts in the soil and measure conductivity. Now, the problem exists in that a lot of references to what is called a saline soil is in terms of a saturated paste. A saturated paste, the salts are much more concentrated, so the numbers are higher than what you would see in most soil test lab numbers. And so the standard that seems to be accepted in what's called a saline soil is a conductivity of about 4 with the saturated paste. But the saturated paste is not the same number as you would see in a 1-to-1 ratio again in a soil test lab. So what do you do with it? Um, you Like I can move on from this slide. I think or this slide. I think I've already said everything on the slide. What you do with this is you can convert those saturated paste numbers to conventional soil test lab numbers. So I took some time one day a couple of years ago and converted saturated paste values to one ratios, um, which approximate the difference between a 1-to-1 ratio to a saturated paste again. And this table then provides a bit of an outline to what crops are tolerant of increasing levels of salinity, as well as some of the visible signs that you might see in a field based on different levels of salinity. So, for example, when we look at a 1-to-1 ratio, generally we start to think of a soil as being significantly saline at about a conductivity of about 2. Um, let's say we have a conductivity of 2.5. We're going to start to see salts, some salts visible on the soil surface at some times of the year. We'll talk about why at sometimes they are there and sometimes not. Um, and we will start to see some reduction of yield. So approximately, for example, as it says here, you start to approach 25% yield loss with wheat and a small yield reduction with alfalfa. And then some suggestions to what crops are most tolerant at those levels. And I'll be sharing these slides. And if anybody wants the table specifically, you can ask me. There are two very important publications that I would encourage you to find. And one of them is very easy to find, and that is The Nature and Management of Salt-Affected Land in Saskatchewan. You should Google soil salinity, salt-affected land in Saskatchewan, and you can quite quickly find this reference online. And you should save it to your computer and you should read it. And if you read this publication published back in the 1980s, you really will understand everything you need to know in terms of soil salinity, as well as a nice section within that publication, Solonetzic soils. There's another publication, the red one on the left, that is much more difficult to find copies of, and I hope that someday someone puts it on a website. I've scanned it, but if anybody wants a copy, I can share it. And this is a work done by, I don't know Mr. Holm's first name, H.M. Holm, but it was a summary of research to look at tolerance of various crop species, including forages, to gradients of salinity within a Saskatchewan landscape. And I'll be referencing this publication in later slides. A publication in 2006 in Canadian Journal of Soil Science took a stab at estimating the geographical risk and to salinity in Western Canada. This publication is as accurate today as it was in 2006. I hate to think that it's a lot of years ago already, but this publication suggested that there are about 2.5 million acres of saline soil in Western Canada and a risk to another 5 to 6 million acres. This is a huge number of acres, and we can take a step back, as I will talk about later, to address some other problems in Western Canada, in particular our supply of forages, that we can use this land much better. And again, this is looking at a lot of acres. Now, since that publication, there has been some changes. There has been some reduction to risk because we have eliminated summer fallow from most of Saskatchewan, most of Western Canada, in fact. And that helps reduce the problem of high water tables. Summer fallow accumulates water and increases the water table within the landscape, and that then brings salts to the surface. We'll describe that in more detail in a few slides. So we have had some reduction of risk of the development of salinity in Western Canada. However, we also, on the other hand, as the value of land increases, I see that farmers often encroaching on marginal land, hoping that that marginal land can produce an arable crop. And that's bad. If we start to try to break up this forages on a saline land, we will then not grow a successful annual crop there, and it also increases the risk of that salinity expanding. A handy tool, a tool that I use, especially in summertime, almost weekly, is SaskSys, the Saskatchewan Soil Information System, led by the University of Saskatchewan. Angela Bedard and her team developed this very handy tool. And if you are not familiar with SaskSys, you should be. We're fortunate in Saskatchewan to have this tool at our hands. The tools in other provinces are not nearly as nimble as SaskSys. Using SaskSys, I filtered for this map, which gives us an indication of where salinity occurs at slight, moderate, or severe levels in Saskatchewan. And we can see across the agricultural landscape of Saskatchewan that there's really no significant regions that don't have some level of salinity risk. And you can zoom in. So this is still SaskSys, and you can zoom in and look at specific soil polygons. So just southeast of Saskatoon, I've got the arrow pointed to a very small polygon here. And without even visiting this specific location, I can see that this is a salinetic and saline soil, a Hanley salinetic soil with salinity class 3, fairly high risk of salinity. I can talk to someone on the phone and understand the salinity risk within this specific region. That's the limit of its accuracy. It doesn't provide the accuracy within a specific field or landscape, but it does provide a good introduction to the risk of salinity in an area. So let's talk a little bit about how salinity develops. It's actually a fairly simple concept. It just depends on scale of geography. So the biggest scale are in these large systems, these large artesian systems, where you have the development salinity over the course of miles, in some cases tens or even hundreds of miles. Now, the example I have here is the Quill Plains. I think if you live in Saskatchewan, at some point you've probably driven past the Quill Lakes, or you've heard of the Quill Lakes. And what is happening within the Quill Lakes is that you have groundwater recharge being the term used to where water is entering the soil. This, again, it's maybe fresh water entering the soil, moving downward through the glacial till. And this glacial till, or the soil within it, is not necessarily saline, but over the course of miles and miles of movement, as that groundwater moves laterally within aquifers, it starts to accumulate salts. Lower landscape, the hydraulic pressure from this artesian system starts to push the water to the surface of the landscape in the lower elevation geography to the point that it actually might create flowing wells. But in the end, as water pushes to the surface and evaporates, salt accumulates. The salt is left behind. And that is what is happening in a large artesian system such as the Quill Plains. Very similar system as when we look at saline seeps over the course of perhaps a few hundred meters within the same field. Again, you can have recharge of fresh water from an upper part of the landscape. That upper part of that water then enters the groundwater, and it will find either an impervious layer or a conductive layer, or perhaps both, allowing that water to move sideways. And if you have a wet year, you might all of a sudden see water starting to seep out of the soil on the lower landscape, or even halfway up a slope, where you might see what we'd almost think of as springs of water coming out of the soil surface. Again, that subsoil might be saline, it may not be saline, but with time, the evaporation loss of water from the lower landscape will start to deposit salts near or on the soil surface. And then on the very smallest scale, we have these types of systems where you might have a slough it might be an ephemeral slough with water only being held there for part of the year. This might be a lagoon, sewage lagoon, or be it from a community or from a livestock, a lagoon. This might be a ditch on a highway that accumulates water at times. Water accumulates, it recharges to the groundwater, and if there is salts in that groundwater, the water and salts will then start to push their way back up to the soil surface, forming what we would call an evaporitic ring. It might be a ring around the entire slough or lagoon, or it might be an edge of salinity developing along the edge of a highway ditch. In the end, a lot of different ways that salinity can occur. It's helpful to understand the magnitude of these systems to help understand if we can or cannot uh, fix the problem as such. Now, groundwater moves up and down, and so salts move up and down. A lot of Saskatchewan has a pretty good snow cover right now, and when that snow cover melts, it will push salts out of the soil surface downward. Well, that's great. It allows you to then seed in a non-saline zone and allow that seed to germinate. Now, salts again can move up and down, and so the impact of salts on a germinating seed bed, the seed germinating in the seed bed, can change from year to year. If we have salts move downward, the seed may germinate. Another year, the salts may accumulate in the soil surface and nothing would germinate. So the impact of salts will depend, especially with annual crops, on the movement of that groundwater and salts within the root zone and within the zone of germination. And so you have varying levels of salts within uh, the landscape to the point that we have to think of soil salinity not just in a two-dimensional landscape, one area being saline or one area not being saline, but really a 3D dimension where we have to consider the depth of the salinity within the landscape. So is that groundwater and the level of salts near the surface or not? Is it near the surface that it will frequently reduce germination of the seed? Is it close enough to the surface to reduce the ability of plants to form an efficient root system? Or can we move those salts to a depth so that there's still salts there, but move them to a depth that they're not in the zone of germination nor in the root zone of that particular crop? Managing that depth of the soil water is very important. Um, I have to address a couple of things to just make sure that we remember some basic soil facts. And first of all, I often see the confusion between pH and salinity. pH and salinity have no direct relationship, so you shouldn't confuse those two terms. Lime can be used to fix acidity, or in other words, increase an acidic pH. Lime will not fix salinity. Gypsum will not fix either salinity nor acidity. It has a net neutral reaction within the soil. Gypsum will not impact soil pH, and nor will it improve salinity. And in the end, there's simply no miracles in soil science. This is a very basic concept of managing soil water and the salts associated with that subsoil water. Are there cures? Again, no, there are no cures. There's no cures for a couple of reasons. One, most of them are not cures. And second of all, there's a tremendous volume of salts involved in saline soil. You could estimate, as an estimate, if you took a loam textured soil with a moderate salinity of about 3 in terms of salinity, that would involve in the range of 8 tons of salt per acre to 2 feet. So even if there was a product that you could buy that would possibly uh, precipitate salts from solution, I don't think there would be a product that you would want to buy to precipitate 8 tons of salts. So it's just simply not a feasible idea to do this. Instead, we have to manage the groundwater and the salts to keep them out of the root zone. First of all, we have to eliminate summer fallow. That's the first thing that we've already talked about and how it can, again, bring the groundwater level down and therefore reduce the risk of salinity. Tillage will increase the risk of salinity because tillage will pull groundwater to the surface. And when groundwater is pulled to the surface, it brings salts. So often I see people tilling saline sloughs. It's a mistake to make. It does not solve salinity. It buries the salts for a couple of days, but in fact, it increases the hydraulic pull upwards of salts to the soil surface. We can remove salts with subsoil tile drainage to leach the salts out, but there's a problem with this in that you have to have water moving towards the tiles for the tiles to remove the salts. So unless you have irrigation to leach the surface soil to bring water down to the tiles, it's probably not going to improve the problem of salinity. I have seen tile situations that might intercept groundwater from moving upwards, but again, this is a problem, a difficult problem to resolve with tile drainage. What I'm going to focus on is not tile drainage. I'm going to focus on using soil water by plants, keeping the groundwater used up to keep it from moving to the surface. And the real solution that can work for pretty much any farm and any saline solution is to grow appropriate crop species. And in this case, it's often forages. There are annual species that can tolerate some level of salinity. Barley is marginally more tolerant to salinity than most other cereals. Canola actually can tolerate a significant amount of salinity if it will germinate. So yes, canola can tolerate quite a bit of salinity, but germinating canola does not germinate, or canola does not germinate very readily in saline conditions. So this whole concept that canola can tolerate salinity depends if it germinates or not. Um, so you have to keep this in mind that there is a range of tolerance, whether it be within annual or perennial species. There's lots of good forage options. Now, some forages are intolerant of salinity. Timothy, red clover, and other species are quite intolerant of salinity. But there's lots of species that have quite a high tolerance to salinity. A couple examples here. Alfalfa is actually quite tolerant to salinity if you can get it to germinate. There are certain species and or selections of alfalfa that seem to be more tolerant to salinity than others. Halo, and I believe that there's other new varieties coming out within the next few years that have some better tolerance. And alfalfa is a nice species to get established in a saline system because it uses so much water and it is so deep rooted that it can be in a very efficient way to reduce the risk of salinity to the surface soil if you can get alfalfa to germinate. A grass species that is very, very valuable, and Jeff Shano talked about it extensively in his presentation, is saltlander green wheatgrass. Saltlander green wheatgrass is valuable for a number of reasons. One, it can tolerate salinity in germination quite well. Two, it has a spreading root system, so it will fill in the space with time as long as you can get some of it to germinate in a saline system. So that's very important because it also makes it more competitive to weed species that can tolerate salinity. So a salt-tolerant grass with a spreading root system will compete against species like kochia or Russian thistle or foxtail barley much more efficiently than bunch grasses. And also, very importantly, saltlander green wheatgrass has good palatability. There are other species like tall and slender wheatgrass and other perennial grass species that have excellent tolerance to salinity, but they're not very palatable. So you need to have a grass that will germinate, a grass that is competitive, and a grass that is palatable to be truly successful within these systems. I like this picture. It tells a story. Pictures tell great stories. This is an example of a field in northeast Saskatchewan. This was a long-term problem of a field that had produced nothing but kochia and foxtail barley for many years. We can see in the background that the farmer has seeded canola still within this landscape. None of the canola is surviving within the right-hand side, even though it was seeded to canola. That's all kochia on the right-hand side. On the left-hand side, the farmer chose to try seeding some alfalfa in the fall. So this is dormant seeding of alfalfa. So dormant seeding requires that you seed the forage species very late in the fall, and you do not want it to germinate in fall. You want it to remain dormant till spring, with the idea that in spring there'll be some snowmelt or rainfall to move salts deeper into the profile, and that seed will be able to germinate. And we see here, even just in the first year production, there's a lot of alfalfa here. There's certainly still forages here, but now we have a system where we have alfalfa. We can cut that alfalfa for hay, which will remove some of the some of the kochia and reduce the risk of kochia from forming seed. And it quickly transforms this landscape. Salinity will have a big impact on weed species. Some weed species can tolerate salinity. Kochia, foxtail barley, Russian thistle are three great examples. Now, it's not that they love saline land. It's just that nothing else is growing there and they can tolerate that level of salinity. Kochia, Russian thistle, and foxtail barley also don't like shade. They don't like crop competition. And so in that saline area where you're repeatedly trying to grow canola or wheat unsuccessfully, you've now created an area of a field that these wheat species, such as kochia and foxtail barley, can establish and can grow without shade. Exactly the sort of conditions that they like. And it becomes a big problem. Now, I don't think anybody on the call here isn't aware that kochia has a problem in terms of herbicide resistance, and frankly, we're not going to spray our way out of kochia problems. We introduce a new herbicide type, a new herbicide group, and within a few years, kochia has become resistant to it. Here's the story in this picture. This is a field that had been repeatedly uh, sprayed with glyphosate, including all the low-lying saline areas, which has really been producing very little crop. We can see a little tiny bit of wheat growing here. It's mostly producing kochia. Sprayed over and over with kochia, or sprayed over and over again with glyphosate to try to kill this kochia. And here we are in fall, and there's a nice green, healthy kochia plant that has survived glyphosate application. That kochia plant's going to form seed. It's going to tumble across the landscape and it's going to deposit glyphosate-tolerant seed, glyphosate-tolerant kochia plants, not just in the saline areas, but in the productive areas of your field and of your neighbor's field. So these areas, these small areas, relatively small areas of saline marginal land, when not properly managed, become really a factory of weed seed production. And probably the most important valuable herbicide that we have going forward in controlling kochia is to stop trying to seed saline areas. And I would add that foxtail barley would fall in the same category. A note on nutrient management, and I'm going to talk quite a bit about nutrient management in saline landscapes. But the first point that I want to make is that the salts in Saskatchewan that primarily cause salinity are sulfate salts. So this offers us an opportunity to manage sulfur within a landscape. If you are in a landscape that is dominated by sulfur or by salinity, you probably need to apply little or no sulfur to your crop. It doesn't matter if it's canola or any other crop. If there's thousands of pounds of sulfur per acre, then you don't need to apply more sulfur. There might be parts of that landscape of a field that is still deficient in sulfur, but this gives us an opportunity to variably manage sulfur application rates. There's often also an accumulation of nitrogen and phosphorus within the landscape, within the saline landscape, primarily because the farmer has been applying nitrogen and phosphorus repeatedly through that area without growing a crop. And there starts to be an accumulation of nitrogen and phosphorus. Because these are also usually in low-lying landscapes, there may be an accumulation of nutrients due to simply past erosion. This example I'm going to show here is work that was done by Ross McKenzie. Ross is retired now from Alberta Agriculture in Lethbridge, but this is a nice example of soil sampling within a saline landscape and how it can impact sulfate levels in a soil test. This is a grid sample within a field near Lethbridge and measured levels of sulfur within that field. Some of the field has extremely high levels of sulfur, well past adequate. Some is marginally deficient and some is sulfur deficient. So within the same field, we have small pockets of saline soil that are that have extremely high levels of sulfur and some areas that are actually deficient in sulfur. And if you look at the numbers from this particular example, if you were to combine all 60 samples from this field, in this grid sample, the average level of sulfate sulfur in the field is 260 pounds per acre. But if I just remove the highest extreme number from the database, the average is 142. If I remove the five most extremely high numbers of sulfate sulfur, the average level is 36. And the end, almost 90% of this field is actually sulfur deficient. And yet there are, on average, is a very high level of sulfur. So this is, I guess, a heads up, a warning that if you are soil sampling within a landscape that has any level of even slight salinity, you have to keep that in mind in terms of soil sampling. So when I look at a soil test, if I see high levels of sulfur in the soil test, my eye quickly will look at the conductivity level in the soil. And even very, very slight levels of salinity will cause this to happen. And then this takes us to the next step in terms of field management. Um, this is a field that I see quite frequently. This field in the picture was seeded to wheat. Next year it would be seeded to canola, and the year after seeded to wheat again. Repeatedly seeding it, repeatedly growing nothing on about 10% of the landscape because of salinity. You can see the salts on the surface here. After a rainfall, the salts completely disappear and it just looks like lovely black soil. Now, I think the solution is pretty obvious in a field like this. You stop seeding, you stop spending money on the saline areas and establish a forage there. It doesn't matter if you need forages or not. It doesn't matter if you have cows or not. You stop wasting money on those areas because you are spending money that will not produce income. And instead, you might be able to make more money by seeding fewer acres, by taking the money that you have wasted in that saline area and perhaps increasing nitrogen rates or phosphorus rates or potassium rates in the productive areas, perhaps using a more effective fungicide or any other means that might be missing from that really profitable part of the field. Easier said than done in some cases. So the picture in the top left, fairly easy to address. The salinity is primarily developed along the edge of the field. And you can see here, well, the canola hasn't germinated. The wheat hasn't germinated very well. Next year, there'll probably be canola on the top and wheat on the bottom. This field in the top is probably fairly easy to address by seeding forages along the edge of the field. The picture in the bottom, not so easy. What does the farmer do here? Probably 50% of this field is not economically productive. But as we talked about in the very first presentation today, these messy areas are not economical. And so we do need to address this. What do we do in this field? Probably at least seed that water runway in the center to a forage, and then try manage around it to make better use of the income on the farm. And as we talked about in the very first presentation today, once again, the probable circumstance that we can grow more crop on less acres. I've got a couple case studies. The first one's I'm going to take a little bit of time on. But and this one is a case study in the Goodale Research Farm at the University of Saskatchewan. This is in dark brown soil, really quite a lovely soil profile here. And this was a case study based on a soil an agronomy lab with Steve Shirtliff's class a number of years ago. And what we did with Steve's lab that year was we all went out into this field on the Goodale farm, and we divided everybody into teams to soil sample the field. Now, in this field, we can see some evidence of salinity. The bottom left, we see a grassy area where there's salts on the surface. Now, this probably tells me that the grassier area isn't big enough. When you seed grass, and I should make this point, when you seed grass in a saline area, you need to seed the grass so it extends a little bit past the saline area. Otherwise, the salts will continue to find their way out past the grassy area. So this grassy area needs to be a little bigger. There's some big patches of kochia here. Kochia is a sign of salinity. This entire grassy area probably could extend to be 2 or 3 times bigger when we look at those huge kochia areas in the bottom part of the landscape. And then along the edge, across from that yard site, there's a big area of kochia. So let's look at what it looks like in terms of uh, biomass production. This is a layered NDVI image, 10 or 12 years of NDVI imagery. And this then becomes a biomass map. And really, in the end, becomes a soil map in this case, indicating where crops are successful or not successful. Now, the blue and green areas are areas of the field that are producing lots of crop biomass. The red areas, very little biomass, and the orange and yellow areas, moderate levels of biomass. We then divided everybody, as I said, into teams of soil sample the field and sampled it in the red, orange, green, or blue areas. But we did send one team out there without a map to simply randomly sample the field. So let's first look at the soil chemistry of the field. We see that under the EC, the 1-to-1 EC, the soil is certainly very saline. The red area conductivity of 4.7 on a 1-to-1 ratio, that's severely saline. Even the productive areas are slightly saline, the green area having a conductivity of 2.3 and the blue area still a slight level of conductivity of 1. There's some irony that the group that sampled randomly actually ended up with a non-saline soil sample. Who knows why? Maybe they just intuitively avoided sampling anywhere where they saw kochia growing. Now, how does this then look in terms of the soil test available nutrients? Well, we see that this entire field has a lot of sulfate sulfur. If I saw the soil sample, I would say, well, you don't need to apply sulfur on this field at all. I don't care if you're growing canola or not. There's no need to apply sulfur here. There's extremely high levels of potassium here. It's very unlikely that you're going to get a potassium response in this field. So then let's look at the phosphorus levels. Quite high levels, an accumulation of phosphorus, especially in those saline areas, again, because the farmer has been repeatedly adding phosphorus in non-productive areas. So we can tone back the phosphorus application rates as well. And then in the nitrate levels, well, there's actually depressed levels of nitrates where the crop has been productive in the past because the crops have been using nitrogen, but an accumulation of nitrogen in the red and orange areas. So then how does this look in terms of crop production potential and recommendations of nitrogen application? Back to the red publication, that book by Holm, published in 1983, where he assessed the sensitivity of crop species to salinity and created a really nice set of equations to estimate yield loss of that wide range of species to the impact of salinity. And the fairly simple equation that is presented in this publication is wheat yield is -10 times by the saturated paste EC plus 100. Using that publication and that equation, we can then estimate yield losses. So the yield loss in the red areas would be for wheat would be over 80%. Significant yield loss of potential within the orange and green areas. Within blue areas, really no significant potential for yield loss. So that's the first step in understanding the right rate of nitrogen. We like to talk about the 4 R's of nitrogen management, and one of them is right rate. Right rate of fertilizer is understanding the yield potential of an area within a field, and then couple that with the amount of nitrogen that can be supplied by the field based on a soil test. So we can then estimate what is actually required for nitrogen fertilizer within this field. The red area, the orange area shouldn't have any nitrogen applied. The yield potential is low. There's a lot of nitrogen already there. Don't apply any nitrogen. The green and blue areas, the ideal rates for the green area is about 56 pounds of N, say 60 pounds of N. The blue area, about 100 pounds of N. The group that sampled this field randomly would have recommended only 67 pounds of N per acre. So we have a problem here. If we don't measure salinity, if we don't sample this field properly, We are going to overestimate the amount of nitrogen on the non-productive areas of the field, and we're going to underestimate the amount of nitrogen required for the productive part of the field. So again, moving those expenses so that we farm the most productive areas of the landscape properly, and let's start managing those unproductive areas differently by reducing fertilizer rates and instead of moving that nitrogen and other inputs into the productive areas, and in some cases, simply growing a different crop species. Because this is all about income. It comes back to what we talked about earlier in the day. The red area, the farm is going to seed it every year. Farming is expensive, fertilizer is expensive, everything's expensive. And the farmer is going to guarantee that they're going to lose money on that acre every year. They might break even in the orange and yellow areas, and they could be making money in the rest of the field if they manage it properly. But if they waste money on the unproductive areas, they'll never achieve the yield potential on the productive areas. So there's really two mistakes being made. There is then the forage solution. Estimating the yield loss within those saline areas of spring wheat to be about 80%, canola close to 90%. There really isn't an annual crop solution for those areas. Alfalfa predicted yield loss about 40%, but then you start to look at saltland or green wheatgrass, and yes, estimated yield loss of almost nothing. And if we think back to Jeff Shano's data earlier in the morning, it took a little while for that saltland or green wheatgrass to establish in the saline areas. But in the end, what do we remember? In the saline areas, the saltland or green wheatgrass was not just as productive as the non-saline areas, but actually becoming more productive because it can tolerate the salinity. It can access that groundwater that is there because of the saline system, and it can access the excess nutrients that have been accumulated in that landscape. So now we go from a yield loss of 80 or 90% of wheat and canola to producing a highly productive, palatable hay species. Have we ever in Saskatchewan or in Western Canada had a hay shortage? Almost every year, almost every year. So we could resolve Western Canada's hay shortage by managing these landscapes better. We shouldn't have to worry about a hay supply when we literally have millions of acres of landscape in Western Canada that can be managed more effectively and better by using forages to not only resolve the saline problem, but to actually stop wasting money, grow more crop on fewer acres, and also produce possibly a palatable and useful hay field on or hay crop on some of these saline areas. I think I have time to look at one more case study, and this is a couple of sloughs. Now, I work for Nutrien, and Nutrien owns land around potash mines, and the two sloughs that I'm going to look at here are two sloughs near the Patience Lake mine, just east of Saskatoon. These were very, very saline sloughs, and the mine wanted to look at solutions to overcome the salinity within these sloughs. Now, there's two sloughs, cleverly called Slough 1 and Slough 2, and we measured conductivity within these sloughs. And look at these numbers. This is the EC and the sodium absorption ratio within these sloughs. Conductivities of extremely high levels of salinity, of over 10, over 15 in some cases in this particular slough. When I first saw this slough area, this is what it looked like. There was nothing growing there. On top of that, the mistake had been made to till the weeds repeatedly and therefore bringing salts and groundwater to the surface. But this was a moonscape with nothing growing the first year that we saw it. So what did we do? Well, you give it a try. You grow some salt-tolerant forages, and you hope for the best. And within a year, this is the two pictures glued together in exactly the same place. Within a year, we had some reasonable good production of grass within this first slough. compared to nothing the previous year. Slough 2 had also significant saline problems. It was not quite as saline, but you have a conductivity of 8 or 10. That's a pretty high conductivity in any soil test. And what kind of success did we have in growing a saline mix of grasses in this slough? It looked like this a year later. The picture on the right is important to see. You can see the salts still on the soil surface. The salts haven't disappeared. And Jeff was asked about this. Can we get rid of the salts? The salts don't disappear. Harvesting this hay isn't going to remove the salts. The forages are tolerating the salts. There is salt still on the soil surface here, but this became a barren landscape to one of very productive hay production. Overall, soil is variable, and we have to accept that. Saline soil is extremely variable. Within a saline landscape, yields are extremely variable. Sometimes we can address this by varying inputs. We can use variable rate sulfur application, variable rates nitrogen that addresses yield potential and nutrient levels in the field based on soil tests. So yes, we can address it that way. Sometimes we just need to vary land use, though, and that may then be varying what species we're actually growing there. I've often said that an economist and an environmental person can meet in a saline slough, shake hands, and agree on everything because you stop losing money. It's a win for the farmer. It's a win for the environment. We provide edge habitat, as we talked about in the first presentation today, which provides edge habitat for pollinators and every other species you can think of. It provides a possible income of hay to the farmer. It reduces the probable emissions of carbon dioxide and nitrous oxides into the atmosphere. And it should be part of the climate conversation in terms of good land management. That's the end of my slides. I think that I might have a minute or two left to answer a few questions if there are any.
Yeah.
I want to thank everybody for sticking with me today. It's getting to be later in the day. And thank you to SIA for having me speak today.
Hey, thank you so much, Lyle. And as you can see on the screen, there's a lot of applause coming, hearts, thumbs up.
They're just glad it's over, man.
And I think I'll save a couple comments right for the end. We do have about 5 minutes or so to go into some questions. And I'm going to start off here. That was in the Q&A. Some, one from Brandon came earlier in the presentation. Does organic matter help prevent surface salinity, such as spreading and incorporating straw rather than baling straw year after year? What would be your thoughts in regards to that?
It can a little bit. Now, most saline areas tend to be quite high in organic matter. There's some irony there because there's nothing growing there. How could it be high in organic matter? It's because the native landscape of salt tolerant forages, we call them forages, but native species, was able to deposit a lot of organic matter in those areas. So they tend to be high in organic matter. So adding more organic matter to a soil that's already high in organic matter might not improve things a lot. By keeping straw on the surface and is valuable to reduce evaporative losses of water from the soil surface because that reduces the amount of salts that are pulled to the surface, as well as that residue. And to be honest, it can even be the mowed residue from kochia to just give some cover to the forage grass as it's germinating and starting to establish. So it can have some benefit, but in terms of in terms of a mulch, but less so in terms of incorporated organic matter.
Okay, thank you very much. And in the Q&A, there's a little bit of conversation. I'm going to maybe jump down to one other question, but there is some good discussion here around freeing calcium carbonates to help replace the sodium ions that have a stronger kind of a calcium +2 charge. There's some conversation. A number of people have weighed in on that, and I'm actually not familiar if some of this conversation, some of the Q&A is available after this conference wraps up. But the one other question to quickly ask here, this comes from Joshua. Does the salt-tolerant forage grass tolerate stress from excess water well? If we attempt to establish forage crops on ephemeral wetlands and the stand drowns every 2 to 4 years, it will be hard to manage or require chemical or mechanical weed control to keep the weeds down. Yeah, what's your thought on that?
Yeah, so that's a really good question because some species don't tolerate flooding. Now, spring flooding tends to be a relatively non-issue. It's summer flooding, if it occurs, it can be a problem. Um, because the actively growing grasses don't tolerate flooding very well. Spring flooding, when the grass species, when the roots and grasses are really dormant still, grasses tend to be able to tolerate those conditions fairly well. A species like, and then a spreading root system grass like saltlander green wheatgrass, and I say that species quite or selection quite often, but and there's others coming from the breeding program at the University of Saskatchewan. But those spreading root systems are really, really valuable to recover from flooding conditions as well. So you do need to keep that in mind, though, that if you have a saline area that is extensively flooded for a long period of time, that it might impact the choice of species that you choose.
Okay, maybe in relation to
Did you
that,
want
we
did you
got
want me to talk about carbonates and lime?
what can you, yes, in say 2 minutes, and there's a couple of other
Yeah, I can
questions
do
that
it, and
will,
I can do it too. I'll very quickly
sure,
address it.
yeah,
So let's not confuse sodic soils dominated by sodium with saline soils that are dominated by calcium and sulfate. So our saline soils in Western Canada tend to be lovely soils. They just have too much salinity. In some regions, saline soils are dominated by sodium, and then you have a problem not just salinity but terrible soil structure, and then you want to use preferably gypsum more than lime to bump that sodium off the exchange complex and improve structure. Um, don't overthink this in terms of our calcium dominated saline soils in Saskatchewan, unless you're talking about salinitic soil, and that's a whole different conversation.
great, thank you. And maybe we've got time for one more here. What's your ideal approach? Oh, no, this other one from Trevor. Is there any problems if the forage is harvested or should it be left?
Well, harvested as needed. I mean, you um, harvest it carefully as you would any forages. There's really no value to leaving it, I don't think. Um, by harvesting the forage, one thing you have to remember, you're not harvesting the salts. You're removing a hay crop that can be utilized for feeding cows or whatever else you want to feed it to. So it can actually be a very, very productive and a very positive economic effect on the farm by selling hay off this land. Absolutely. Harvest the hay if you need to.
Yeah, even as you mentioned, this aspect of having hay shortages really year over year, and in some ways, perhaps there is enough acreage of our prairie landscape that could, in
Oh,
fact,
absolutely.
produce a decent amount of hay.
We should have a larger cow herd in Saskatchewan to be able to consume the hay that could be produced in saline areas.
I'm really taking note both of the time, noticing that any of the conversation that is really around managing as a part just from units of land, quarter section, 80 acres or whatever, really thinking about the landscape. Uh, that's really generating a lot of the response from participants here. So you've definitely brought a great amount of experience and wisdom here. I want to say thanks on behalf of the SIA. I'm glad I'm not answering these questions and that you are, but I found it really informative. And I just want to thank you for the work you did in preparing this presentation, in offering this to us. Um, I do want to make note here that this is the end of today's program, but there is a whole lot of good stuff coming up tomorrow as well. So just want to invite everyone to join us at 9:30 tomorrow morning. Use this same link to join. And again, Lyle, thank you so very much for your presentation. Really
Thank
appreciate
you
it.
for having me, and thanks for everybody for participating today. It's great.